This is Friday, January 8th, 2021, Physics CP. I'm teaching about static electricity today, and I'm going to go ahead and record the more of the class session so that you guys can play this back to your heart's content as many times as you want. Even after you graduate. Oh, that's so exciting. So the topic that I'm teaching is about static electricity. In a previous episode, I introduced the idea from chemistry class that when you look at the periodic table, you might remember that atoms are made up out of protons, neutrons, and electrons, that the nucleus is where the protons and neutrons are located. The nucleus is uh, deep inside the center of an atom. Neutrons don't even have an electrical charge, so we're not going to worry about them in this unit. Protons have a positive charge, but they're stuck in the nucleus, so they don't move when we consider what's going on with electricity. The electrons have a negative charge, and they are the ones on the outer electron cloud. Those are the ones that we can move, remove from an atom, or add to an atom. When we remove it from an atom, the atom becomes positively charged, and we call that ion a cation. When we add electrons to an atom, it becomes negatively charged, and we call that an anion. And no, I don't pronounce this cation, even though it's tempting to pronounce it that way. I call it a cation. All right, so there are formulas and numbers that we can put to our study of static electricity. The charge on a single proton is, in metric units, 1.602 times 10 to the negative 19th power coulombs. A coulomb is a unit of electrical charge. Welcome back. Now, suppose you want to put this into your calculator. If you have a Casio, I'm sorry, I'm not really going to be able to help you. You need to consult the owner's manual. If you have a sibling who also used a Casio and knows how to use it, I see. Okay. The charge on a proton is 1.602 times 10 to the negative 19th coulombs of charge. If you want to store that on your calculator memory, if you're using a TI graphing calculator, I would suggest you type in 1.602 second EE. Please don't use the times 10 button for this stuff. Get in the habit of using the proper notation style. And it's not just that, the proper way of representing an exponential number. 1.602 second EE. Now, there's an exchange key. On a TI, it's next to the decimal point on the bottom row, 19. On the bottom left part of your TI calculator is a button called Store. This means take whatever number you've been entering, and you're going to store it into a memory position on your calculator. The memories on a TI are letters of the alphabet. So you have to type or press the alpha key, the green one near the top left of the calculator, and that will change the cursor to flashing a letter A, which means, okay, I am ready for you to tell me which letter of the alphabet you want me to use as the memory location for this number. Well, you got some choices here, right? You can use the letter P for proton, You could use C for charge, which I don't recommend. You could use E for electron, which I also don't recommend. So I will suggest that you use the letter P, which on a TI is above the number 8 key. Press the Enter key. And now the charge on one proton is stored in your calculator memory. Anytime that you need to use this number and you want to recall it, you press the alpha key and then the letter P, and ta-da, it's there. You don't need to bother with the Enter key until you're done with the expression that you're building. Great. Now, the charge on an electron is equal in magnitude and opposite in sign to the charge on a proton. So the charge on an electron is negative 1.602 times 10 to the negative 19th power of coulombs. You would be using the quantity of charge when we're calculating the forces between two electric charges. Coulomb's law is the equation for calculating the electric force between two charged objects. The equation is lowercase letter k, which is called Boltzmann's constant, times Q1 times Q2 divided by R squared. Boltzmann's constant, K, has a value of 8.99 times 10 to the ninth power newtons meters squared per coulomb squared. Now this number you're going to be using every single time that you use Coulomb's law. The charge on the proton you would only use if there's a physics problem that says, oh, I have 27 protons or I have 13 electrons, and you need to convert from number of protons or electrons into a quantity of coulombs of electric charge. So this number, Boltzmann's constant, out of these two choices, if you were only going to put one of these into memory, definitely the K is the one that you should put into memory. 8.99 second EE 9, the store button, the alpha key, and you should really pick a logical letter that represents Boltzmann's constant. You could put a B for Boltzmann. You could put a C for constant. But I really suggest maybe you should use the letter K on your calculator. Of course, you can use any letter of the alphabet. Be careful if you choose something like X, because that one tends to be overwritten on a TI during calculations. So maybe not quite every letter of the alphabet is a good choice. Fine. Back to Coulomb's law. The K is Boltzmann's constant. The F is the electric force between any two electric charges. Q1 is the electric charge in coulombs on the first electrically charged object. Q2 is the charge in coulombs on the second charged object. And R is the distance in meters from the center of one charged object to the center of the second charged object. When we make up physics problems to practice the skill of doing this stuff, I'm trying to do two tasks at once here. Often our charges are expressed in coulombs, or Greek prefixes of fractions of a coulomb. 25 coulombs of charge is approximately how much electricity is in a lightning bolt. That is a lot. So often, to be realistic, we're dealing with millicoulombs. Milli means 1/1000th of a coulomb. That's still relatively a lot of electric charge. So sometimes we deal with microcoulombs. A micro is 10 to the negative 6 coulombs of charge. Even nanocoulombs, which is 10 to the negative 9th power, in this case of coulombs. If we give you some number of protons or number of electrons, then you have to convert them to coulombs using this factor here. 1.602 times 10 to the negative 19th coulombs per proton, or negative that amount, coulombs per electron. So as we make up problems, if I call on you, your choices are from this list. So if I say, gee, I'd like you to make up the number of charge on Q1, you could tell me, oh, charge 1 is going to be 580 protons. Okay. Or you could say, oh, no, charge 1 is going to be negative 32 millicoulombs. Okay. Of course, the Greek prefixes go below nano and above, kilo and mega. But I think this is a reasonable range for what we would be encountering in an electronics shop. When you touch a touch screen, you're really dealing with maybe even picocoulombs, 10 to the negative 12th coulombs of charge in the detector that says, oh, that's where your finger is located on the screen. All right, so let's at least practice a problem. And I'm going to call on some random student in a moment. I'm pretty sure your sound doesn't get recorded. I'm going to activate my earbuds anyways. And adjust my speaker volume if I need to. Oops, wrong button. Yeah. Okay, random volunteer. Tell me about charge Q1, Anuj. Positive or negative, number of protons, number of electrons, or how many coulombs in charge? Ah, I'm sorry. I realized I made a tactical error. I now call on Josh V. All right, that's a very small quantity. And by the way, you can only have integer numbers of protons or electrons. Just like in chemistry class, we can't deal with 2/3 of an electron or 1/3 of the charge on the proton. Now, when you get to college, of course, then you can deal with subatomic particles that make up protons and electrons, where yes, they actually do have 2/3 and 1/3 electrical charge. But Q1 today is 3 electrons. Tell me about charge Q2, Daniel. Whoops, I'm sorry. Tell me about charge Q2, Tyler. I don't know. You're the one telling me. Interesting. All right. And now I need to know something about, uh, on this practice problem, let's just deal with the distance between them. And by the way, these Greek prefixes can apply to distances as well as to anything else. Seconds of time, meters of distance, along with grams of mass, right? We can have milligrams, micrograms, nanograms, milliseconds. Wow. All right. So tell me about the distance between these two electrons, Sean. Was that 2 or was that 20? Okay. Well, that is a tremendously large distance for tremendously small amounts of electrical charge. Students, power up your calculators and calculate, please. What is the force of electrical interaction between 3 electrons and 6 electrons that are separated by 2 meters? Why do you not take notes, child? Coulomb's law states the force of electrical interaction between any two charged objects is the product of Boltzmann's constant K times charge Q1 times charge Q2 divided by r squared, the distance from the center of one charge to the center of the second charge. And as long as I'm displaying the equation, I want to also remind you that if you get a negative answer, that means they attract each other. If you get a positive answer, that means they are repelling each other. All right, I'm now going to randomly pick on Tanrusi. Have you been able to calculate the electrical force yet? Excellent. I'm going to stand by and wait until you have a response. Well, then you are obligated to share with us your different result. What did you get? So the second student thinks the answer is 1.04 times 10 to the negative 27th power. Again, the units should be newtons. This is a significant difference. The first one is a very big number relative to the second one, which is a very tiny number. So I'm going to call on a third student. So here's how I would have solved this problem. Of course, we're going to be just plugging it into Coulomb's law equation. Everything to the right of the equal sign is given. So K Q1 Q2 over R squared is the formula. Because I took the trouble to store K in my calculator memory, and I also took the trouble to store the charge on one proton in my calculator memory, that makes it a lot simpler to enter it in my calculator as alpha K. And unfortunately, I have to write it as a capital letter because you don't have a lower lettercase choice on a TI. For charge Q1, it's 3 electrons, and for charge Q2, it's 6 electrons. I notice that electrons have a negative charge and electrons have a negative charge. And I'm multiplying electrons times electrons. So I'm multiplying a negative charge times a negative charge. They're going to cancel. A negative times a negative is a positive. So I didn't bother typing in a minus sign twice. Instead, I only entered it once. We have our 3-minute break. All right, here's how I came up with the answer. On my graphing calculator, I typed in alpha K. For 3 electrons, I typed in 3, then alpha P to multiply it by 1.602 times 10 to the negative 19th power. That converts it from 3 electrons into some teeny tiny amount of electric charge in coulombs. Then I typed in 6 for 6 electrons. Again, the letter P from my calculator memory to convert these 6 electrons also into units of coulombs of electric charge. That's the entire numerator right there. Divide by the distance from the center of one to the center to the other was 2 meters. So 2 x squared button, meaning square the value of r, enter. So I'm hoping you see that if you bother using your calculator memory to store constants, it does make the task of putting these numbers into your calculator go very easy, or relatively much easier, and you're not making a mistake as easily. Meaning, if you have to always type in 1.602 times 10 to the negative 19th instead of just alpha p, wow, here it's 2 keystrokes, here it's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 keystrokes to represent the same number. 10 versus 2. All right, so I agree. I got an answer of 1.04 times 10 to the negative 27th power newtons, a very teeny tiny one. Oh boy, this is so much fun. Let's do a second one, everyone. And the second one, we're going to turn it around just a little bit. So, Nathan, what is the charge Q1 on the second problem? Aw, kids, always so teeny tiny. And Zara, what is the charge on Q2? Aw, kids. And now, instead of asking what is the force, or actually asking the student to randomly come up with the distance between them, I'm going to ask a student to randomly come up with the force between them. Jonathan H., what is the force of repulsion between charge Q1 and charge Q2? No units? Wow, that is a teeny tiny force. But as we've seen from the previous example, that's on the order of forces for situations on this scale. Great. So now the challenge is, what is the value of R separating 3 protons from 20 protons if we measure the force of repulsion is 2.23 times 10 to the negative 16th power newtons? Of course, you have to use Coulomb's law, but this time you need to rearrange it to solve for R. Take a moment and work it out. And do you know what units that would be? Okay, does anyone agree with that? Yes, I see two hands in agreement. And on my calculator, I got the same result. So, by the way, you could use a Greek prefix for the 10 to the minus 6. 10 to the minus 6 is called a micro. So this is 7.88 micrometers, which in common terms, we call those microns. So 7.88 microns. To get that, by the way, you should have algebraically first multiplied both sides of Coulomb's law by r squared. Then divide both sides of Coulomb's law by F, the force. And finally, take the square root of both sides. That means R was the square root of K, Q1, Q2 divided by F, all of that underneath the radical sign. Okay, I panicked because my alarm went off, but that was not the end of the period. So I'm going to hustle now and start teaching you the new content that I was really hoping you would learn this unit this school year. The new unit deals with the situation when we have more than just two electric charges. So I'm going to start with a simple geometry exercise that says, look, suppose I have a force here, F1, and it's going to the right with 10 newtons of force. And over here, I have a force F2, and it's pushing to the right with 5 newtons of force. And over here, I have a force F3, and it's pushing to the left with, I don't know, 3 newtons of force. I think the way I'm setting this up doesn't really make much sense. Let me get rid of this and say, look, I have a force of 10 newtons pushing this object to the right. I have a force of 3 newtons pushing this object to the left. The net force on this middle object would be 7 newtons to the right. Okay, that one should make sense. Now, in the name of teaching you something exciting and new, I'm going to pull out a sheet of graph paper to use with you. Wow, I recognize this sheet from the beginning of the fall semester. Whoa, but it's still a sheet of graph paper that I can use for educational purposes. So I'm creating a new situation. I have charge Q1, and I'm going to make up the numbers because I'm in too much of a hurry. So I'm going to say charge Q1 is 18 millicoulombs of charge. I'm using graph paper, and I'm going to set the scale where each grid is 1 meter. So, boop, 1, 2, 3, 4, 5 meters to the right. I'm going to put charge Q2, and this charge, oh, I guess I could ask a student. Jaden, positive or negative? And some random integer number. I will do that part. Just give me some random number. Okay. And I am going to make it units of millicoulombs. Yes. Negative 25 millicoulombs. All right. Fabian, how many meters to the right do I go to get to the third charge? How many squares? Okay, 1, 2, 3, 4, 5, 6, 7. Sadly, this looks a lot like the same example that students had yesterday. Joseph Q, what's the charge on this one? Positive or negative, and some integer number of millicoulombs? Okay, now in this situation, I have 3 point charges. They're all in a straight line, which means this is going to be a one-dimensional physics problem. The problem becomes, what is the net force acting on the charges? But the answer is going to be different for each one of the 3 charges. So I have to ask myself, which charge should I solve for? And in the problem, someone's going to have to say, oh, either Q1 or Q2 or Q3. Pick one. I'm going to just say Q1 in this example that we're doing. So bear with me. The question becomes, what is the net force on Q1? To solve this problem, of course, we have to use Coulomb's law. F equals K Q1 Q2 divided by R squared. But this equation only has 2 charges in it, yet this problem has 3 charges in it. You might become foolishly tempted to just multiply Q1 times Q2 times Q3 and divide by, I don't know, average or something for R. That would be a wrong way of doing this. The correct way to do a problem like this one is to shut off all of the charges. So I'm covering them up with my hand, just shut off. Turn on the one charge that you're supposed to be solving for. That would be Q1. Okay, keep Q1 turned on all the time for the rest of the problem. For all the other charges, and in this example, there's only 2, but there could be 5, 6, 8 different charges if I wanted to be cruel to you, right? One at a time, turn on each of the other charges. So I'm just going to work left to right. I'm going to turn on charge Q2 and put these 2 charges into Coulomb's law and calculate the force of attraction, in this case, because they're opposite signs, the force of attraction that is pulling Q1 to the right. I'm going to figure it out and write it down. After I come up with that result, I'm going to shut off charge Q2 and turn on the next charge, in this case, charge Q3. I put these 2 charges, Q1 and Q3, into Coulomb's law. Be careful to use the correct value for R. It's 5 meters plus 7 more meters is the value of R to go from Q1 to Q3. So I'm going to be using a value of 12 meters. With the correct value of R, you plug in Q1 and Q2 into Coulomb's law. These are both positive charges, so they're going to be repelling each other. In this case, you're going to be calculating how much Q3 is pushing Q1 to the left by repulsion. Calculate that, write it down. After you've gone through each of the charges one at a time, look at the forces that you calculated for each pair of charges. Add them up as vectors, and that will give us the final answer, the net force on Q1. I'm going to go ahead and do this at ludicrous speed. Here we go. Shutting off charge Q3. I'm going to calculate charge Q1 and Q2. So the force between charge Q1 and charge Q2 is going to be K Q1 Q2 over R between 1 and 2 squared. So I'm starting to use subscripts to represent which charges I'm working on. I'm working on charges Q1 and Q2. Into my calculator, I'm going to type in K 18 on my calculator on a TI, I would actually type second EE negative 3, but here I'm just going to write it in scientific notation. So times 10 to the negative 3 coulombs times, if you can keep track of the minus signs in your head, that's great. If not, then you need to put in the exchange key. 25 times 10 to the negative 3. That's the entire numerator. Divide by the distance from Q1 to Q2 is 5 meters. So 5 squared. Enter. Why don't you students do this and see if I agree with your answer? Ronaldo, let me know when you have an answer, or share with us what you get. Yes, I agree. So 161,820 newtons, but there's a minus sign, and that means pulling Q1 to the right. Now ponder things for a moment, kids. Normally, when we set up an x-axis on a sheet of graph paper, the positive x-axis is to the right, and of course, the negative x-axis is to the left of 0. In this problem, we get a negative force, but based on the geometry, that means it's pulling it to the right, of course. Attraction means it's going towards Q2. So this minus sign does not mean it's going in the negative x direction. This minus sign means it is pulling Q1 to the right. And by the way, from the point of view of Q1, this same attractive force is pulling Q2 to the left. So you have to take the point of view of which charge you're standing on as you look at things. Great. Now the process is shut off Q2, turn on Q3, and we're going to calculate the force of interaction between charges Q1 and Q3. That's going to be K times Q1 times Q3 divided by the distance between charge 1 and charge 3 squared. Of course, that's going to be K times 18 millicoulombs times 20 millicoulombs divided by 5 plus 7 meters squared. Calculate, please. Newtons. Okay, so one student's got an answer of 19,150 newtons. A second student got an answer of 22,475 newtons. And I got an answer that agrees with the second student. Okay, and what's more is it's a positive sign because they're both positive charges. So this is repelling. I'm not going to spell it. Repels Q1, pushes Q1 to the left. Now, I've gone through all the charges. It's time to tally up what's going on. I'll do it visually a little bit, not to scale very much. I've got 161,820 newtons. I did that wrong, didn't I? Whoops. Maybe I should do this to scale. Let's say if I go by, I'll go by 50s. 50, 100, 150, 160. Okay, so I have 161,820 newtons pulling Q1 to the right. Separately, I have 22,475 newtons pushing Q1 to the left. To find the vector sum of these two vectors, which I try to do to a rough scale of 50,000 newtons per grid space, I see they're going in opposite directions. So I need to take the mathematical difference of these two numbers, 161,820 minus 22,475, ignoring all the rules of sig figs for the moment, I get a net force of 139, and let's finally round it off to 3 sig figs, 1,000 newtons to the left. 139,000 newtons to the left. So if I were to say on a coordinate system, what is the net force? To the left is minus x direction. So be careful. I would write it out just to make it clear. That says, oh, okay, I understand the arrow. I did it wrong, didn't I? No one's going to correct me, are you? The big arrow's to the right, the little arrow's to the left. and this is to the right. Now that one is the end of the period. Great. And to stop recording.